Now let's continue our discussion from last lecture. Last lecture, we focused on renal clearance. That means the model had a big assumption that the renal or the kidney filtration or clearance is the only mechanism that the drugs can be eliminated in the body. And then we got the equations we got last time. And then today's lecture is an extension from the last lecture. So we call the plasma clearance. The plasma clearance, we give it a symbol called Q, plasma, and it is defined as the total rate at which a drug is irreversibly removed from the plasma through all elimination pathways. So if you want to see like how Q plasma may look like, it is a sum of a bunch of possible elimination mechanisms. It can be metabolism in the renal. Renal was just one of the one of the 10 renal, which we discussed last time. Then sweat, biophysis, and anything. So then when we have this Q plasma defined, we can still build the mass balance for the body. So we can still draw the same diagram. I'm not going to draw it again. So now in the diagram, we have the body, and instead of the kidney, we can say like it's a collection of all possible clearance mechanism. Then we have mass balance. Let's still call it mass balance. I would like to refer to like mass just to refer to the drug. Mass balance in the body. So the analysis remain exactly the same. The only thing change is we replace Q renal with Q plasma in this case. So we have V apparent. If you forgot about what we discussed last time, make sure you review last video. So V parent multiplied by C total dC total dt now equal to minus Q plasma C total. That's all we need, and we still have the same initial condition. So we can define the first order elimination rate constant for each pathway elimination pathway. So define first order constant for each elimination pathway. So we can use index I to refer to like for example the ith pathway. Then you can define it's the ith pathway's elimination rate constant is Ki. So little case K equals to Qi. Qi is the respective rate, clearance rate for that pathway divided by V apparent. Now we can sum over all elimination routes, and then we can say the total elimination rate constant. First order elimination rate constant. We call the K total, little place. So this K total is written as the sum over I of all Ki. Well, since all the Ki, we know its expression is 1 over V apparent multiplied by sum over Qi. Well, sum over Qi is nothing but Q plasma. So we had the first equation in this lecture is just the sigma Q is just a Q plasma. This result isn't surprising. You probably have guessed it at the beginning. It's by the construction. So K total is Q plasma divided by being apparent. So now we can write our equation in terms of K total. So we have dC total dt equal to minus K total multiplied by C total. Well, the two totals are different. The total, the subscript for K total, the total means all the elimination pathways. But the C total, this total refer to the total drug concentration in the plasma, which is the bound and unbound concentration. So they have two different meanings, but somehow they call it total anyway. And we have initial condition means C total at t equal to 0. Okay, now solution solve for C2. Just integrate this equation, the governing equation, integrate it once, and you will get the general solution and a constant of integration, and then you use the initial condition to determine the constant of integration. I think we have gone through a detailed example in the very beginning of this course when we talked about the conservation laws, and I think we used some bacteria population and we solved this initial condition in detail. So this is the basic tool. If you forgot about like solving this, you can revisit those early lectures and any mathematical class you've taken, the differential equation class and revisit that. So make sure you know how to do this. So we solved for C total, we can got C total not multiplied by exponential minus K total multiplied by T. Okay, that is our equation, our solution. So if the dosage is given, so if the total dose is if the dose given, so we call it D drug, then the C total not the initial condition is just a D drug divided by V apparent. This is This is for rapid injection. Because only for rapid injection, the immediate concentration of the drug in the plasma is the same as drug divided by the apparent. If you refer to the three types of curves, we had absorption, which you start from zero and then have a peak. The second is let me just draw it here in case you forgot. So this is concentration versus time, and this is absorption. And this is rapid injection, and then the third one is like infusion. Three types of like drug, like taking drug mechanism, the method. So it's only, so this equation only works for rapid injection, because only one for this time, you know that your initial concentration is the maximum, which is given by the dose divided by the apparent. Otherwise, for example, for absorption, the initial concentration is actually initial concentration is zero, and in that case, we cannot say C total zero equal to this one. So this is limited to. So for the rest of our discussion, we will just focus on rapid injection. Because this gives us a initial condition that we can relate to drug dosage. Otherwise, we need additional like treatment tools. But right now, assuming rapid injection give us some like simpler initial condition that we can illustrate through this equation. Okay. So now let's look at a concept called area under the curve. Area under the curve, it's well, let me put this math curve. It's AUC. We have 0 to infinite. That's a full name of this. So what does area under the curve mean? So for example, for this line, I'm drawing. Okay, so let's look like this one. For the rapid injection, this is the area under the curve. And by definition, you see what it means. It's the area under the curve, 0 to infinite. It is defined by integration from 0 to infinite over time. You have the concentration C total is a function of time, dt. So this integration depending on both the dose and the drug's clearance rate. The meaning of this, like the significance of this, is this quantifies the total drug exposure of the body. So let me put it down. It quantifies. So drug exposure of the body. So if you integrate the concentration over time, it gives us an idea that over the time from 0 to infinite means if you take a dosage and then it will decay exponentially. Eventually you don't need to integrate over into infinity, but like theoretically, let's just say from the time that a drug is taken to infinity far away. So what's the impact of the drug in the body? Then, well, we need to consider its concentration because like the response of the drug, response of the body to the drug, we have learned it before how we have the equation. It's a function of the concentration. So in order to know how the drug does to the body, then we integrate it over time. So that's what it means. Now for this particular problem, for this definition of area under the curve is generic. So now for rapid injection. Injection means we can use C total, not the initial condition, as a quantity that's related to the drug dosage. We have A U C. So now we can like substitute our concrete expression for C total. You integrate it, and then after integration, you will find that it equals to C total divided by K total. And verify it on your own. You just do the integration. You will need this type of like practice to like develop a familiarity and understanding of this material. Sometimes your understanding need you get your hands dirty. It's not just listen to the lecture and feel like, yeah, I understand that. You will get a different level of understanding if you like get your hands dirty and do every calculation like on your own. Okay. Now let's replace C total not with D drug. So we have D drug divided by V apparent multiplied by K total. Remember that we can express K total in terms of Q plasma and V apparent. So this is the equation that I'm referring to. Using this equation, you can continue to write it as D drug divided by Q plasma. Okay, this is our final expression. This expression, if you look at it, it's very intuitive and elegant and also suggestive of what you may think about it. Okay, what's the total impact of the drug on the body? Of course, it's proportional to the dosage, the drug, and it's inversely proportional to the plasma clearance rate, because the higher the drug can be cleared out of the body through multiple mechanisms, the lower the impact. So the final result is totally makes sense. And if you for example you reinvented the wheel, you do this on your own, you derive your equation from the beginning on your own, And at the end, when you obtain this equation, you should feel happy because you feel, yeah, this makes sense. Hopefully, you can also develop intuitive understanding of what's going on here. Okay, now let's also introduce what is biological half-life. I'm sure you have heard about half-life millions of times. In other classes you have taken, including some exposure to science in high school. Half-life, you might, depending on the classes you have taken. So you might have like heard about like the nuclear reaction or the half-life, the type of things. And basically it means how long does it take for something to take impact so that the impact become 1/2. So now the biological half-life is called T1/2. Maybe let me write it down. It is the time required for the drug concentration to reduce to half of its initial value. So E is the time for the drug to reduce to half of its initial value. Basically, says, okay, C total at a time, T1/2 divided by C total not. Maybe let me do this way, T equals to T. When T is evaluated at this, it gives you 1. Then we can just use our analytical expression for C total. Just plug in. You will get that C T total, so T1/2 equals to logarithm of 2 divided by K total. You can express K total in terms of V apparent and Q plasma. V apparent multiplied by natural log of 2 divided by Q plasma. And also look at this, try to develop some intuitive understanding. So this is proportional to V apparent. That means the larger volume, the distribution volumes that the drug exists in the body, the longer time it will take for it to reduce to 1/2. It makes sense. And it's also inversely proportional to Q plasma. That means higher elimination rate would lead to a lower half-life. It also makes sense. So this is about the biological half-life. So I would suggest you go through this derivation again and then understand the relations between different variables, and then as you practice of this like derivation and the process, then you can start to look at the homework problem that will help you to get familiar with using these equations. So many of our homework problem is not necessary to be like challenging. So some of the problem were pretty straightforward. I mean, like throughout the entire lecture, some of the problem were pretty straightforward in terms of like you just plug in the numbers, and just by plugging the numbers, actually just do it for once or while, or for once or twice, and it helps you to develop a understanding of using the equations, and then that eventually helps you to master the material. Okay, the problem says a drug is administered as a rapid injection with a dose of given. The plasma concentration immediately after injection is given, and the concentration falls to a level after 2 hours. So it has several parts. The first asks you to determine the apparent volume of distribution. The second is the elimination rate constant. The third is plasma clearance. Then determine biological half-life and then area under the curve. All right, that's all for this topic.